Hello, I would like to welcome you to lecture 12 of 3N03. We'll continue our discussion of applications of operational amplifiers, and I will show you here in this lecture a number of applications related to comparators, level detection, outbounding, analog to digital conversion, and summing amplifiers. And we'll take it from there to we'll have one more lecture to finish the OpAmp applications, and then we'll move on to transistors. Okay, before starting to discuss the applications of OpAmp, I thought that you need some background about binary applications or binary words. In electrical engineering, we use binary logic, which means that the memory that we have in our cell phones, it contains large number of cells, and each cell is really a capacitor. And this capacitor is either charged or discharged. When the capacitor is discharged, we say it has a logic of 0. It has a logic of 0. When it is charged, we say it has a logic of 1. So it has two binary states. Either it's charged or discharged. And the way it's stored in the memory, it's stored in the form of words. So you can have a large number of these words. This is this one here. Try this one. So you have a large number of binary words. This one word actually here, and it can have any binary sequence 1 0 1 0 0 1 1. So each one of these is called a bit. We call it a binary digit, a bit. Okay, and it's really nothing but a capacitor. And when we combine a number of these together, we call them a byte. A byte when we have 8 of these. We can call it a word when we have 16 of these together. Sometimes you use 32 of these bits together, but use them to convey information. And each one of these binary digit has, if you want to convert it to a corresponding analog number or a corresponding value, we give it a certain weight. This is the least significant digit. It has a weight of 2 to the power 0. This is the first one. It has a weight of 2 to the power 1. The second one, 2 to the power 2, and so on. The next one, 2 to the power 3, 2 to the power 4, and so on. So if you want to get the corresponding value of this number, it's 0 by 2 to the power 0 plus 0, 2 to the power 1 plus 0 to the power 2 will give you 0. This one here is a binary word 0, 0, 1. I'm here assuming that I'm using only 3 bits. But in reality, we use 8 bits or 16 bits or 32 bits. I'm just showing them for illustration. The value of this binary digit or binary word is 1 by 2 to the power 0, which is 1, plus 0 to the power 1 plus 0 to the power 2. So it's going to be 1. And this one will have a value of 2. This one, 0, 1, 1 will have a value of 3, and so on. So you could see, as these binary numbers count in this way, the corresponding value of this binary word keeps on increasing. And so this is a binary representation of our decimal numbers. So 0 is represented by a word of all zeros. 1, you will have 1 only in the least significant digit. 2 will have 1 in the second least significant digit, and so on. 3, you'll have 2, the two least significant digits or bits are equal to 1, and so on. So this is how this will count. Here we have 3 bits, so we can count up from 0, 0, 0 up to 1, 1, 1. It's not that difficult to see that these are 8 numbers. So you can get 8 numbers out of a binary digit, of a binary word with 3 bits, because 2 to the power 3 is equal to 8. So this is very useful. This is the binary word representation, and this is a corresponding decimal number representation. And of course, there are also hexadecimal representation. There is also octal representation. But for now, for this course, I will focus only on the binary words. So just to keep in mind what the basic things. A bit is nothing really but a capacitor. It's either charged. So when it's charged, it will say it has a logic value of 1. And when discharged, it has a logic value of 0. We combine these bits together if 8 of them, we call them a byte. 16 of them, we call them a word. You can have words with 32 bits or 64 bits. So the larger the number of bits, the higher the corresponding decimal number it can represent. Every binary word has a corresponding value. we get this corresponding value by multiplying the value of every digit by the appropriate exponential power of 2 here. And we use this one again in our computer. This is what our computers contain: sequences of zeros and ones. This is how information is being sent over the internet. And on the other side, they take these numbers, they convert them to corresponding analog values, maybe using a calculation very similar to this one, and then this is how they can process them in analog fashion, but they are usually transmitted in a digital form. One of the applications we'll see here in this lecture is the analog to digital conversion, and this is what happens when you speak, say, on Skype to one of your friends. Your voice is really converted by the mic into an analog signal. Okay, it's an analog signal, and every value for this analog signal here, every level corresponds to a binary word. So, for example, if you reach this level here, if the signal, if your voice is too low, then the corresponding word is going to be sent as 0, 0, 0, 0. If your voice, the amplitude of your voice go a little bit higher, so the sample, it of course is being sampled. They sample your voice at a certain rate. It has to be a certain sampling rate to guarantee accuracy, and then this value here will be 0, 0, 1, and so on. So as you are speaking, your voice is being sampled. So they take this sample, this sample, this sample, this sample, and this sample, and so on. And each one of these analog samples, analog values, is being converted to a corresponding binary word, and then sent over the internet, and then Skype or any other audio program will convert the corresponding digital numbers into analog numbers, and then deliver it to your speaker on the speaker on the other side. So this is a very important step. We use it very often now, because all of the sensors we use in our life, like you're using stress sensor or strain sensor or temperature sensor, all these sensors collect binary data, and then these analog data, and these analog data are being converted into corresponding binary words, and then this what submit to computers, and this what computer is going to process. One other application that we're going to be using in this course is digital to analog conversion, which is the opposite operation. So here you have you are giving a digital word, number of digital words. So when you receive a digital word, you have to convert it to a binary signal, but the amplitude of the binary signal will increase as the corresponding value of this binary word increases. So I agree that this one will have a value of 0, this will have a value of 1, this one will have a value of 2, this one will have a value of 3, value of 4, 5, 6, and so on. So the digital to analog conversion does the opposite. It takes a binary word and then it converts it into an analog signal. Of course, it can create a form of a staircase approximation, but this can be smoothed out through a capacitor or some integration circuit. We can make this one way smoother. So you just remember what's meant by analog to digital conversion. We convert an analog signal received by a sensor into a digital signal that can be processed by the computer. Digital to analog conversion, we convert the digital signal created by the computer to an analog signal that can be submitted, say, to a loudspeaker, or it can be submitted to any other output that requires an analog signal. Okay, the first application we'll discuss in this lecture is a comparator. Comparator, as the word says, it's simply comparing two signals. It's using the OpAmp to compare the input to the positive input, the positive terminal, and the input to the negative terminal. Here, the negative terminal is kept at ground. So when the positive terminal exceeds 0, remember this is 0 here, positive terminal exceeds 0, the output will saturate at VCC, at the highest possible voltage allowed for this OpAmp. Say it can be 5 volts or minus 5 volts, 15 or minus 15. So it will saturate at the largest allowed voltage. This can be 5, 15, or 10, whatever the case may be. And here for this circuit, they pass it along to a differentiator. So every time there is a rising edge, the differentiator will create a spike. There is a falling edge, the differentiator will create a negative spike. And then they use this one to trigger a square wave form here on the other side. So the comparator simply creates a binary either VCC or minus VCC, depending whether the positive terminal is higher in voltage than the negative terminal or not. It's simply comparing them, and as we agreed, the gain of the op-amp is infinite. And this is why when the positive terminal exceeds the negative terminal, the output would saturate at VCC. When the positive terminal drops below the negative terminal, the output will saturate at minus VCC. And here this is a supply voltage connected to the comparator. Okay, let's take a look at this example. We have here an op-amp. It is connected to a power supply of values 10 volts and minus 10 volts. The negative terminal is kept at 0 volts, and we apply the positive the input at the positive terminal, and the input is nothing but a sinusoidal waveform of amplitude plus 5 volts. And we'd like to determine the output of this circuit. Every time the input is positive, it exceeds the negative terminal. Negative terminal is grounded, remember. Then the output here will go to plus 10 volts. Will saturate at plus 10 volts. Remember, the gain is infinite, but realistic op-amps cannot create a voltage that goes beyond the supply voltage. So the maximum output will be plus 10. When Vn is negative, so it drops below the negative terminal voltage, which is 0, then the output will saturate at minus VCC, which is minus 10 volts. Because the output, as we agreed, is equal to A multiplied by V plus minus V minus, but the gain is too high. For practical op-amp, the gain is 10 to the power 6, 10 to the power 5, so this will cause the op-amp to saturate at the lowest supply voltage. So, as I explained in the previous slide, this is what you're going to be getting when V plus is higher in voltage than V minus. The output saturates at the maximum allowed voltage, 10 volts. When V plus drops below V minus, the output saturates at the least allowed output voltage, which is minus 10 volts, and so on. So we use this one to create a square wave from a sinusoidal waveform. This is by using this comparator functionality of the op-amp. In the previous circuit, I used to compare to a voltage of 0, but this does not have to be the case. For example, here I'm comparing the positive terminal to a battery of value V reference. So when Vn exceeds Vref, the output will saturate at plus VCC. When Vn drops below Vref, the output will saturate at minus VCC, as shown here. So this is here plus VCC and minus VCC, the maximum allowed output voltage and least and minimum allowed output voltage. One other way of creating a non-zero comparator, you can see, is to create a voltage divider here. Remember, there is no current flowing into the negative input terminal of the op-amp. So here the voltage at this point is nothing but this voltage multiplied by R2 over R1 plus R2. So, and this is a fixed value. This is a fixed value. It's our VREF, our reference voltage. So when Vn exceeds this number, you get the output will saturate at VCC. When Vn drops below this voltage here, the output will saturate minus VCC. Another way of creating also a non-zero level detector is to use Zener diodes. Here, remember, a Zener diode, this is a positive voltage, so the Zener diode here is really reverse biased. But if this voltage exceeds the Zener breakdown of this voltage, then this Zener diode will break down, keeping the voltage between this point and the ground equal to V Zener. So if this Zener is equal to 5 volts, then the voltage between here and here is equal to 5 volts, and the current going through the Zener will adjust itself such that the resistor R will absorb the rest of the applied voltage. So in this case, we are comparing the positive terminal voltage to V Zener. And V Zener here is our Vref, and you get exactly the same output waveform. Okay, let's take a look at this example. We have here a comparator circuit. We have the op-amp, and we have the supply, the input voltage, and the input voltage is a sinusoidal waveform. It's oscillating between 10 and minus 10. The positive terminal is connected to this voltage divider. The voltage here is 5 volts, and this is 3 kilo ohm and 2 kilo ohm. So what's happening is very simple. Remember here, I'm connecting here to the negative terminal, not to the positive terminal. So I'm comparing always V negative to V positive. So when the input voltage exceeds the Vref, the voltage here, then the negative terminal will have a higher voltage than the positive terminal. Then the output will saturate at minus 15 volts. Remember, I'm applying the input here to the negative input terminal, not to the positive input terminal as the previous figures I've shown you. I picked this one specifically different to show you the difference. So so when the input exceeds the voltage here, then the output will drop to minus VCC. So as the input, if the input exceeds certain value, the output will drop to minus VCC. Now when V minus drops below this reference voltage, then the output will saturate as at 15 volts. So the output is either plus 15 or minus 15. Now, what is the reference voltage? Reference voltage is simply equal to this voltage here, which is the voltage across the 2 kilo ohm resistor. So it's equal to 5 multiplied by 2K over 2K plus 3K. So this is our supply voltage. So I'm always comparing this number here to 2 volts. So the reference voltage here is simply equal to 2 volts. So when V input exceeds 2 volts, the output will saturate at minus VCC, which is minus 15 volts. When V minus drops below 2 volts, then V plus becomes higher than V minus, then the output will saturate at plus 15 volts. Remember that the supply voltage here is 15 and minus 15. So this slide shows the calculation I told you about. The reference voltage is the voltage across the 2 kilo ohms, 5 volts by 2K over 2K plus 3K. This will give you 2 volts. So when Vn exceeds 2 volts, the output will saturate at minus VCC, which is minus 15 volts. When Vn drops below 2 volts, the output will saturate at plus VCC, which is plus 15 volts. And you know why it saturates? Because the OpAmp has infinite gain. But you cannot get an infinite voltage. You can only get the maximum allowed voltage by the supply that you have. So if you try to plot V out and Vn, this is V out here, the red line, okay, and this is Vn. Notice there is 108 degrees phase shift between them. When this is maximum positive, this one is maximum negative. And the reason for that is because I'm applying my input to the negative terminal. It's a little bit different from the theory we explained earlier. One application that we see very often is trying to create a comparator with hysteresis. So the comparator is comparing 2 voltages, but I would like it to act differently when it crosses, when the signal has some sort of noise imposed on it. So for example, here we have this Vn. So when Vn exceeds a certain upper voltage, okay, upper voltage, then the output will drop to the maximum negative value. And regardless of the other oscillations happening in the input, it will stay at this number, okay? And even it drops below this one again, it will stay at this number, and then it goes below a certain another level called VLOW threshold here, or VLOW trigger point here, and then when it drops below that number, the output will go up to the maximum voltage. Notice that when it exceeded the upper value, the output changed, but when it dropped below the upper value here, the output did not change. So this is called hysteresis. It does not follow the same level by increasing or decreasing your voltage values. One of the interesting circuits we used for hysteresis is called the Schmitt trigger, and the theory of this circuit is achieved by using this positive feedback. We have here a positive feedback. Look what's happening. Assume that V out is positive. V out is positive. Then the voltage here at the positive terminal is simply a voltage divider. So it's equal to V out multiplied by 10K over 10K plus 47K. So I'm comparing Vn to this V out, to this voltage here, V plus. This is a positive number. So when this one exceeds that positive number, okay, what's going to be happening? The negative terminal will have a higher voltage than the positive terminal. Then the output will go to minus VCC. The output will go to minus VCC. When the output goes to minus VCC, now you are comparing to a completely different voltage. You are comparing to minus VCC multiplied by R2 over R1 plus R2. You are comparing to this one. Okay, so now the voltage will change again unless Vn drops below this number. So the output will stay at its minus VCC value until Vn drops below this number. It follows exactly the same figure I've shown you earlier. So when Vn drops below minus VCC multiplied by R2 over R1 plus R2, then V plus will have a higher voltage than V minus, then V out will change to VCC again. And when that happens, you are comparing now to VCC by R2 over R1 plus R2, VCC by 10K over 10K plus 47K. So you're actually comparing to a positive voltage. So Vn, the output will not change unless Vn rises again until it exceeds that positive voltage. So you can see it does not follow, it changes only when Vn exceeds this upper voltage and when Vn drops below this negative voltage. This is a positive value, this is a negative value. And this is called Schmitt trigger. Schmitt trigger meaning it's a comparator, it's making a comparison between the output and the input, but it allows change only when these two levels are crossed, when Vn exceeds this positive number and when Vn drops below that negative number.